Welcome to our journey into the microscopic world of atoms. Today, we are going to explore a fundamental principle in chemistry known as Hund's rule of maximum multiplicity. If you have ever wondered why certain elements behave the way they do, or why some materials are magnetic while others are not, the answer lies in how their electrons are arranged. By the end of this video, you will understand exactly how electrons choose their places within an atom and why nature always prefers the path of maximum stability. Let us dive in. To understand how electrons behave, imagine you are getting on a public bus that has several empty double seats available. Naturally, you will choose to sit in an empty double seat all by yourself rather than sitting right next to a stranger. Only when every double seat has at least one person in it will new passengers start sitting next to someone else. Electrons behave in the exact same way when they are filling up the seats or orbitals inside an atom. Because electrons all carry a negative electrical charge, they naturally repel one another and want to stay as far apart as possible. This simple, everyday logic of avoiding crowding is the perfect way to understand atomic structure. Now that we have our bus analogy in mind, let us look at the formal chemical definition. In chemistry, this behavior is known as Hund's rule of maximum multiplicity. The rule states that for a given electron configuration, the lowest energy arrangement, which is the most stable state, is the one with the greatest number of unpaired electrons with parallel spins. To break this down, when electrons enter a set of degenerate orbitals, which are orbitals that have the exact same energy level, they will first occupy empty orbitals singly. Furthermore, all of these single electrons must have the same spin direction, usually represented as spin up. Only after every orbital in that subshell has one electron will they begin to pair up with a second electron of opposite spin. You might wonder why we care so much about how electrons sit in their microscopic seats. The arrangement of these electrons directly determines the magnetic properties of the element, which is incredibly important in real-world applications. If an atom has unpaired electrons, it is paramagnetic and will be attracted to magnetic fields, which is why materials like iron are magnetic. On the other hand, if all electrons are paired, the atom is diamagnetic and weakly repelled by magnets. Furthermore, Hund's rule helps us understand why certain elements are highly reactive while others are stable, guiding the creation of everything from industrial catalysts to the batteries in our smartphones. This brings us to the mathematical side of Hund's rule. Nature always prefers the arrangement that makes the spin multiplicity as large as possible, because a higher multiplicity corresponds to a lower, more stable energy state. The formula for this is m equals 2s plus 1. Here, m represents the spin multiplicity, which is a measure of the number of possible quantum states for the system based on its spin. The symbol s represents the total spin quantum number of all the electrons in the subshell. Each electron has a spin of either plus 1/2 for spin up or minus 1/2 for spin down. To find s, you simply add up the spin values of all the unpaired electrons. As s increases, m increases, leading to greater stability. Beyond just spin, there is another reason why parallel spins are favored, and it comes from exchange energy. This formula shows how we calculate it. EEX equals n times n minus 1, all divided by 2, multiplied by k. EEX stands for the total exchange energy, which is a special stabilizing energy that occurs when electrons with the same spin are in degenerate orbitals. The variable n represents the number of electrons that have the same parallel spin, for example, all spin-up electrons. The symbol K represents the exchange energy per pair of electrons, which is a constant negative value, meaning it lowers the total energy of the atom. As the number of parallel spin electrons increases, the number of possible exchange pairs increases rapidly, making the atom incredibly stable. Before we move on, let us see this with a concrete example. Let us determine the most stable electron configuration for the 2p subshell of a nitrogen atom, which has an atomic number of 7. We are given 7 total electrons, and we need to find the arrangement of its outermost electrons and calculate its spin multiplicity. The first 4 electrons fill the lower energy orbitals, leaving exactly 3 electrons for the 3 degenerate 2p orbitals. Following Hund's rule, we place 1 electron in each of the 3 orbitals with parallel upspins. This completely avoids any electron-electron repulsion within the same orbital. Next, we calculate the total spin s by adding the plus 1/2 spin value of each of the 3 unpaired electrons, giving us a total spin of 3 halves. Now that we have our total spin, we can find the multiplicity. We plug our total spin s equals 3 halves into the spin multiplicity formula, m equals 2s plus 1. The 2's in the numerator and denominator cancel out perfectly. This leaves us with 3 plus 1, which gives a final multiplicity of 4. This is the absolute highest possible multiplicity for 3 electrons in a p subshell. Physically, this mathematical result proves that placing the electrons singly with parallel spins is the most stable, lowest energy configuration for the nitrogen atom. It perfectly illustrates why nitrogen behaves the way it does in chemical reactions. Let us look at another example to see what happens when we run out of empty seats on our atomic bus. We will determine the electron configuration for the 2p subshell of an oxygen atom, which has an atomic number of 8. After filling the lower orbitals, we have exactly 4 electrons left to place in the 3 2p orbitals. According to Hund's rule, we first put 1 electron in each of the 3 available orbitals. Because there are no empty orbitals left, the 4th electron has no choice but to pair up with one of the existing electrons, adopting an opposite spin. In that first orbital, the plus 1/2 and minus 1/2 spins cancel out to 0. Adding the remaining 2 unpaired electrons gives a total spin s of exactly 1. Continuing with our oxygen atom, we now substitute our newly calculated total spin s equals 1 into the multiplicity formula. M equals 2 times 1 plus 1. This simple calculation gives us a final spin multiplicity of 3. Even though this multiplicity is lower than that of nitrogen, it is still the maximum possible multiplicity for 4 electrons in a p subshell. The physical interpretation of this result is fascinating. Because oxygen has 2 unpaired electrons remaining, it is a paramagnetic gas. This means that liquid oxygen is actually attracted to magnets, which is a direct, real-world consequence of Hund's rule in action. Now that we have calculated the configurations, let us visualize them. On the screen, you are looking at the orbital diagrams for both nitrogen and oxygen. On the left, the nitrogen diagram shows 3 square boxes representing the 2p orbitals. Notice how each box has exactly 1 upward pointing arrow. This perfectly illustrates the electrons occupying empty orbitals singly with parallel spins to maximize stability. On the right, the oxygen diagram shows what happens with 1 additional electron. The first box now contains both an upward and a downward arrow, representing paired electrons with opposite spins, while the other 2 boxes still hold single unpaired electrons. This visualizes exactly how Hund's rule dictates the filling order to achieve maximum multiplicity. We have covered a lot of ground today. So let us summarize the most important ideas. First, Hund's rule of maximum multiplicity is nature's brilliant way of minimizing electron repulsion and maximizing stability within an atom. Second, we learned that by filling degenerate orbitals singly with parallel spins before pairing them up, atoms achieve their lowest possible energy state. We saw this mathematically through the spin multiplicity formula and visually through our orbital diagrams. Finally, this simple principle dictates the fundamental architecture of the elements and explains their magnetic behaviors, like why liquid oxygen is attracted to magnets. You now have the key to unlocking why elements react, bond, and behave the way they do. Great job completing this topic.